Sound good?
Yep, sounds good.
All right. Good morning, everybody. I'm David Rodriguez. I'm a grad student in the Material Science and Engineering Department. I'll be talking to you today about my thesis topic, which is molybdenum-based conversion coatings for aerospace aluminum alloys. Start off with a brief outline of what I'll be talking about today. Start off with my objective of my research, then go into an introduction on why it's important and why we need to pursue this further. Go into the experimental section, and we'll start off with the characterization of my coating, and then go into the repassivation characteristics of this coating, and this is what makes it the most important and will be the most vital part of my experimental section. We'll go into results and then end with a conclusion and summary. Okay, so my objective is to replace chromate in chromate conversion coatings, which are used to protect aerospace alloys, with molybdenum, which is less toxic than chromium and will be more beneficial for people applying this coating to airplanes to protect it. All right, so introduction. Aluminum alloys are very important to the aerospace industry because they have a high strength to weight ratio. So they're low density compared to steel, but with alloying elements, they can be comparative with the strength of steel. But with the added alloying elements, we get an increased rate of corrosion with aluminum alloys because we do not have the aluminum oxide layer rapidly forming on the surface of the alloy. So we need to coat this with something to prevent it from corroding on the airplane. And it has been known for over 100 years now that chromium as an additive to an alloy or a coating for an alloy can reduce the corrosion. And what is used industry-wide in the aerospace industry is chromate conversion coatings. These have chromate as an inhibitor, hexafluorozirconate as an activator, and potassium ferrocyanide as an accelerator. Now I will replace the chromate with molybdate in order to make this more environmentally friendly. Now, why is chromate conversion coating so important to the industry? Well, here's a model of how they form chemically. So on the base layer of the aluminum alloy, you have chromium-3, which provides a barrier layer. And then on top of that, you have the majority of the ions forming at chromium-6, which has very unique properties. So we have the barrier layer to start off with. Then we have a bipolar layer. So since we have the two valencies, we have a layer that is formed that will prevent cations from migrating off the surface of the metal and prevent anions from leaching into the surface and corroding the alloy. Now, the problem with this is they are very toxic. They are restricted in California to 0.06 parts per billion in the water. It has been shown widely in industry that they increase the statistical probability of cancer to the point where it has to be removed, and workers who are exposed to it are warned of the hazard of being around it. Okay, so the most important mechanism is the self-healing or repassivation mechanism. Now what we have here is an open circuit potential diagram where you have the initial noble potential, and then when it's scratched, it drops in potential to the corrosive, or to a more active potential that is seen on the base aluminum, and then it heals itself to the original more noble potential. What happens here is in this animation, you have the scratch forming that damages the two layers and into the base metal itself. Now you have the corrosive solution coming in, and you have aluminum hydroxide forming, and this causes the more electronegative chromium-6, or not electronegative, but more wanting of electrons chromium-6 to migrate across this scratch and fill this in, and this reforms the barrier layer of the chromium-3 on the scratch surface of the aluminum alloy. Now, my experimental section will discuss on how I coated the samples and the actual sample preparation. Solution preparation was done with the base formula of the accelerator, passivator, and the molybdate as the passivator. And concentrations for these three components were decreased by half to find an optimal solution that was used for the rest of the studies. Now the coating, what we have here on the left is a polished aluminum sample, and on the right we have a coated sample with the molybdate-based conversion coatings. The coating approximately took 7 minutes and each surface was polished of the aluminum sample before it was exposed to the coating bath. Here are the results. The main things for the corrosion resistance was the open circuit potential and polarization. Open circuit potential measures the voltage at equilibrium of the reactions. So the corrosion reactions that are going on in a salt solution are measured and a voltage is given off based on the number of electrons that are given off from the reaction. And polarization is done by supplying a voltage plus or minus this open circuit of minus 0.75 volts and plus 0.75 volts. And the current corrosion was measured as well as the voltage. Okay, here's a typical open circuit potential. For all samples, once the salt solution was added, it would stabilize around 20 to 120 seconds. This one stabilized at about 25 seconds. And here we have a polarization curve for the optimal formulation that I had found. There were others that had slightly better corrosion parameters based on the data acquisition software that we had, but these formulations had low adherence and will be shown in a later section with SEM imaging as to why we did not choose this sample. This one has an I-core of about 0.3 actually, average for these three samples. And here it is compared to the aluminum alloy. As you can see, we have a definite shift in the open circuit potential and the I-core just from adding the coating to the aluminum alloy. This is important because this shows that we have protected it and will be used in further research. Here are the SEM results. Here is a plain aluminum sample that has been polished, and down here we have one that is coated. The coating is hydrated, so when it is exposed to the vacuum of the SEM, it does become cracked and look like mud almost that has dried out in the sun. Now, keep in mind this morphology for the next slide. Here we have one formulation that did have better corrosion resistant parameters, but you can see it has been almost stripped clean off the aluminum alloy surface. And on the bottom, we have the optimized formulation where we have some spallation of the coating, but it remains mostly intact when you compare it to this. Okay, Raman spectroscopy results. Now, the important thing to realize is we want to actually have the chemistry characterized of the coating to see if we have a model similar to that of the chromate conversion coating. And here we have multiple peaks of, that show where the molybdenum has formed. We do have MO double bonds and stretching modes that show that molybdate has in fact formed on the surface of aluminum alloy. Here we have the sodium molybdate curve. This is one of the components in the coating bath, and we have one peak that matches up, but the reason it doesn't match up for the other two is we have different bonding modes that would be seen in just a typical salt. Now here we have the base aluminum alloy, we have FTIR spectroscopy results, and on the bottom we have the polished uncoated sample, the sodium molybdate salt, and on the top we have the coated sample. Now from these two graphs we can interpret where we have certain peaks on this curve, which we have blown up right here. We have some that are attributed to aluminum oxide, and we could tell this from the unpolished or the polished sample. And then we have water, and this is known. This is seen in our FTIR spectra because we have a hydrated coating. And then these peaks over here are for the molybdenum oxide. Okay, for XPS results, we did sputtered and non-sputtered. So what sputtering is, we removed about 40 nanometers from the top of the coating, and this exposes the underlying layer, which tells us the different chemistry at different layers, which we could propose a model for. So for the initial one, the non-sputtered sample, we have two species, one at 6+ and one at 5+ for the molybdenum compounds. And then when we sputter 40 nanometers, we have the addition of two more species. And these ones are at the 3+ valence. And this goes to this percent composition table. So before sputtering, we have the majority of molybdenum 6+ at 82%, and that drops to less than 30% after sputtering. Then we have the majority of the coating at the 40 nanometer depth, or approximately 41%. Now this leads us to compare back to the original model shown for the chromate conversion coatings, where we have the different species present in 2 different layers. From there, when you compare the valencies, you have the chromium 3+ and the chromium 6+, and here you have molybdenum 4+ and molybdenum 6+. Now this leads us to believe that we will have the repassivation behavior. So how do we test this? Well, we take the coated sample and scratch it in a solution of 0.05 molar sodium chloride and measure the open circuit potential, and then further we will characterize the chemistry of the coating. Okay, so here we have the open circuit potential. This is where it's scratched, and similar to the previous graph that was shown in the introduction, we have it returned to the more noble potential, and this was scratched a second time, so it dropped again to the base aluminum value, and then went to the noble potential again. So this shows that it's corroding less and still protected by the molybdate-based conversion coating. This is Raman spectroscopy mapping. What we have here is, this is the sample area in this red box, and these are contour maps of the sample. This peak at 960 wave numbers is indicative of just molybdate regardless of its valence. So we have some minor decrease in intensity in the scratch area, and at 480 wave numbers, this is more indicative of a 6+ valence. And you can see that there is definitely a absence of the 6+ within the scratched area that you see here in the micrograph. Okay, summary, 12 different formulations were created, and one was found to be the optimal formula that we used for the rest of the coating process and the characterization. Here we have the uncoated sample, which had an E-core of approximately minus 739 millivolts, while the E-core of molybdate-based conversion coatings had minus 573, and chromate conversion coatings have minus 550. Now the I-core isn't as great as the CCCs. We have 0.1 for the chromate conversion coatings and 0.91 for the molybdate-based conversion coatings, but that can be improved through further optimization. Conclusions: SEM showed that we do have a coating formed on the aluminum alloy. Raman, Fourier, transform infrared spectroscopy, and XPS both showed that we have molybdate compounds on that. And with XPS, we found that we have a multi-layer structure similar to that of chromate conversion coatings. Now, based on this, we have found that we have something very similar to chromate conversion coatings, and with the repassivation techniques, we found that we have something that has the self-healing mechanisms that chromate conversion coatings have as well. And with the Raman spectroscopy, we were able to characterize this chemically and show that we do in fact have molybdenum within the scratch. Here are my references and questions.
You showed that the layer tends to dry out under vacuum. How susceptible is it to drying out under more ambient conditions?
More ambient conditions, it remains intact. I've had some that have been lying on my workbench for a while, and even under the microscope now they have a very intact coating. But when you take it from the SEM, you could still see some cracking under microscope, just optical microscopy.
Does that lead to other modes of corrosion?
It would if it was exposed to vacuum, but when it's just ambient air, it doesn't crack like that.
What about at 36,000 feet? If you're coating airplanes, that could be a problem.
That could. But at 36,000 feet, you're not going to have 10 to the minus 6 torr that...
It's lower pressure.
Yeah.
The effect is...
The fact that, well, with a typical layer for the airplanes, it goes the chromate conversion coating as the base layer, and then there is a polymeric paint on top of that, and then a sealant. So it should reduce it from being exposed to the elements of low pressure.
Thank you.